Hello! In this video, we're going to be discussing why infinity divided by 2 is not equal to infinity in the context of Pascal's wager. First, why even spend time on such a weird and esoteric topic? Well, I will illustrate via a dialogue with the atheist guy with a hat. Ahem. Hello, Mr. Atheist. You should become a Christian. Oh, hello, Squared. Why is that? I take the probability of Christianity to be something like 1 in a million. Well, imagine a game where I roll a dice, and if it lands on a 6, you get $600. Otherwise, you get nothing. How valuable is this game? What is its expected utility? Well, it's the $600 times the 1 in 6 chance, which equals $100. The expected utility of this game is $100. That sort of mathematical reasoning about rewards and probabilities falls under a branch of mathematics called decision theory. Now, let's apply decision theory to religion. If you do become a Christian, and Christianity is true, then your reward is infinite. And infinity times 1 in a million is still infinite. So you should be infinitely motivated to become a Christian. If you want to run that argument, it appears you'll have a problem. I myself think Islam is less likely than Christianity. So instead of a probability of 1 in a million, it has a probability of 1 in a billion. But when I multiply the infinite reward that Islam promises by 1 in a billion, the expected utility calculation still yields infinity. So both Christianity and Islam have the exact same expected utility, infinity. So there's no reason why I should become a Christian rather than a Muslim if I am to listen to you. Well, no, you definitely should become a Christian. You yourself said you found it to be more probable. Isn't it obvious that going with the more probable religion is the solution here? Squared, what's obvious to me is that I should not dedicate my life to religions that I myself find to be improbable. You want to claim otherwise on the basis of decision theory. You want me to ignore my common sense based on what mathematics says. But what the mathematics says is that Christianity and Islam have equal expected utility. You can't have it both ways. Either I stick with my common sense and live my life as an atheist, or I go with what the mathematics says and find that all religions are equally worth believing in. Well, at the very least, the mathematics says you should pick some religion, right? You shouldn't stay as an atheist. Well, no. There's an itsy-bitsy tiny probability that there's a god who will give an infinite reward to only atheists for some reason. When I multiply the probability by infinity, I get infinity. So remaining an atheist also has an expected utility of infinity. When you use infinity in decision theory, everything breaks, and all options have the same expected utility of infinity. So I think we simply shouldn't include infinities in our decision theory. Anyways, that's all I have to say, and you couldn't think of a more natural sounding way to script this conversation's ending, so goodbye. Oh, bye. Okay, so we have this problem. Anything times infinity is still infinity, so the reasoning in Pascal's wager ends up assigning an expected utility of infinity to anything with a probability more than 0. The point of this video is that the statement anything times infinity still equals infinity, also called the absorption property of infinity, is actually false in the context of Pascal's wager. Infinity times 1 in a million is actually a bigger number than infinity times 1 in a billion. But wait, I hear you say, I've learned from mathematicians that infinity does have the absorption property. Well, the important point that is usually missed in discussions about Pascal's wager is that there are a lot of different kinds of infinity. There are infinities from set theory, calculus, set theory, topology, set theory, and so on. Some of these infinities have the absorption property, whereas others don't. So if we're going to include the notion of infinity in our decision theory, we ourselves need to pick the infinity that makes the most sense. Standard decision theory usually only includes real numbers, so when we want to extend decision theory to include infinities, we need to decide which kind of infinity we'll use, because each infinity has different properties. This involves a bit of interpretation on our part. But there happens to be one concept or type of infinity that works super well with decision theory. So I'm arguing here that this type of infinity we should use in our extension of decision theory. And when we use it in Pascalian reasoning, the probability of a religion ends up being important. I want to actually explain what this type of infinity, actually is, but before that, I want to look at some other possible types of infinity that you might suggest using in decision theory and explain why they don't work well with decision theory. Disclaimer, I'm going to be giving an intuitive explanation of all these different kinds of infinities rather than mathematically rigorous formulations. With that out of the way, let's jump into this. The first kind of infinity that we'll look at is infinite cardinalities. If you're a fan of William Lane Craig, chances are you've run into these guys before. The idea is that set theory is the branch of mathematics that deals with collections or sets of things. Like you could have the set of prime numbers, or the set of the numbers 1, 2, and 3. Now, set theorists want numbers that describe the size of each set, so they invented cardinalities. If a set contains 100 numbers in it, then its cardinality is 100. If a set has 200 things in it, the set's cardinality is 200. But the set of all natural numbers, 1, 2, 3, and so on, is infinitely big, so we need an infinitely big cardinal number, Aleph null. Now, in set theory, the definition of a set's size is somewhat counterintuitive because it's defined in terms of us being able to pair off the items in each set with none left over. For example, if I have a set with the numbers 1 and 2, and a set with the numbers 7, 8, and 9, I could pair off 1 with 7 and 2 with 8, but then 9 is left over from the second set and can't be paired off with anything else, so the second set is bigger. That might seem fine, but when we extend this to infinite sets, stuff gets a bit weird. If you take the set of the natural numbers and the set of the even numbers, we can easily pair each natural number with the number that's twice as big. Since we've managed to pair off all the numbers, they have the same quote-unquote size. They both have a cardinality of Aleph null. But intuitively, the second set is half as big as the first one. So the idea is you can double Aleph null or divide Aleph null by 2 and you still have Aleph null. Aleph null is thus defined as an infinity that possesses the absorption property. So should we use infinite cardinalities like Aleph null in our extension of decision theory? Well, there are a couple of reasons to think that we shouldn't. First, there are clear cases when using an infinity with the absorption property gives us the wrong answer in decision theory. Imagine there are 2 buttons and you can only press one. Button A has a 99% chance of giving you an infinitely good reward. Button B has a 1% chance of giving you an infinitely good reward. If we modeled this situation using Aleph null as the utility of an infinite reward, then both options have an expected utility of Aleph null. But obviously this is wrong. Button A is clearly better. In the skit at the beginning of this video, the atheist guy with a hat said that conclusions like this are just what the mathematics says, but that's not true. These kinds of bizarre conclusions only arise if you make the decision to model our extended version of decision theory with an infinity like Aleph null. But no one is forcing us to use Aleph null rather than some other kind of infinity. This decision is up to us, and Aleph null's failure to give the correct answer in this scenario is precisely why we should decide to use a different infinity. Here's another reason that using cardinalities like Aleph null for decision theory is sketchy. The equation for expected utility, simplifying a bit, is the utility of an event times the probability of that event. The example I used earlier was getting $600 times 1 in 6. The utility can be any real number, and the probability can be any real number between 0 and 1. A real number times a real number is a real number, so all of these are real numbers. For example, a utility of 1.3 times the probability of 0.6 equals an expected utility of 0.78. However, the cardinalities do not include real numbers. No set includes 1.3 items in it. The cardinalities are completely different kinds of numbers from what standard decision theory uses. So if we try to rewrite our equation here and make utilities cardinalities instead of real numbers, we lose the ability to make normal statements of decision theory. Breaking decision theory is what we're trying to avoid, so again we should probably use some other infinity. Let's now turn our attention to another type of infinity, the ordinal numbers. These are sometimes confused with the cardinal numbers, but they are different. The idea of ordinals is that once you have a set, you can order the items in it. For example, if you take the natural numbers, you can order them from smallest to largest. The first item is 1, the second item is 2, the third item is 3, and so on. Now the ordinal numbers are actually these things, the first, second, and third. An ordinal just describes where something falls in a set after you've ordered it. Now, even though we've ordered this set from smallest to largest, there are other ways to order sets as well. For example, we could start by ordering the odd numbers from smallest to largest, and then place the even numbers after the odd numbers from smallest to largest. In this ordering, the first number is 1, the second number is 3, the third number is 5, and so on. But what about the number 2 here? Where is it in the ordering? Well, it's the infinitieth number in our set. Its ordinal is called omega, and 4 has the ordinal omega plus 1, and 6 has the ordinal omega plus 2, and so on. So since we can order the elements in an infinitely big set in weird ways, we need infinitely big ordinal numbers to describe the placements of the items in those sets. Now, we could also order sets so that they look like this. You have A, B, C, and so on infinitely, then P, Q, R, and so on infinitely, then X, Y, Z, and so on infinitely. The ordinals would be first, second, third, and so on, then omega, omega plus 1, omega plus 2, and so on, 2 times omega plus 1, and 2 times omega plus 2, and so on infinitely. So what this means is that the ordinal omega times 2 does not equal itself. It equals an ordinal that's twice as big. Therefore, ordinals do not have the absorption property. But before you try to extend decision theory with ordinals, there are some things you should know. Firstly, the ordinals do not include real numbers either. There is never a 3.7th number in a set's ordering, so we still break standard decision theory. Also, multiplying an ordinal by a whole number like 2 is easy enough to define, but multiplying an ordinal by a real number like 0.37 is difficult to define, so we've doubly broken our decision theory equation because we can't easily multiply ordinals by probabilities. Another problem that applies to both cardinals and ordinals is the issue of subtraction. Even though omega plus 1 is indeed an ordinal, omega minus 1 isn't an ordinal. Neither is omega minus omega. They're just undefined, like dividing by 0. Similarly, aleph null minus aleph null is also undefined. But this doesn't bode well for decision theory, because you sometimes want to take the expected utility of a positive outcome and subtract off the expected utility of a negative outcome. So these infinities do not make good candidates for extending decision theory. Another infinity you may think of is the infinity of calculus. Here's one example. The limit of the function f of x equals 1 over x as x approaches infinity is 0. Now, what is this kind of infinity? Well, one day a mathematician wrote down, as you put bigger and bigger numbers into the function f of x equals 1 over x, the result gets closer and closer to 0. But since he was a mathematician, he was very lazy, and so he came up with a shorter way of writing it. This shorter way of writing it happened to use a sideways 8 style infinity. But in reality, that infinity is not a number. You can't apply addition or subtraction to it, you can't do anything with it. It's just part of the syntax that he decided to use so that he didn't have to write as much. And I guess it's okay syntax because it conveys the idea of getting bigger and bigger, but don't let it confuse you into thinking it's a number. There's just the function with the property that it gets closer to 0 as bigger numbers are put into it, and purely by convention, we use the sideways 8 infinity symbol in part of our description of this fact. That's it. Now, another sort of statement you might see is something like the function g of x equals x as x approaches infinity is infinity. This one is so misleading. For a statement like z equals aleph null, mathematicians aren't being lazy here. They're just telling you that z is some number, and this number is aleph null, which happens to be infinite. But in the calculus case with g of x, even though there's an infinity on the right side of the equation, it's not a number either. Again, some mathematician just wanted a quicker way of writing down the fact that as you put bigger and bigger numbers into g, the output gets bigger and bigger as well. This isn't saying that the function equals an infinite number, it's just describing what the function does. Obviously, if the infinity of calculus isn't a number, then it can't be used in decision theory. Okay, so we've looked at 3 types of infinities that cannot be used in decision theory. Finally, we'll look at the kind of infinity that can be used in decision theory. Surreal numbers. Here's the best intuitive explanation I could come up with of the surreal numbers. When you were young, you were taught the natural numbers, 1, 2, 3, and so on. But then you learned you could extend this number system with subtraction, and you get the negative numbers as well. Then you learned that you could extend this number system again with division, and get the rational numbers, the fractions. Then you learned that you could extend the number system again and get the numbers which aren't fractions either, like pi. Well, the surreal numbers are yet another way of extending the number system. The way you can define a new number in the surreal number system is by giving me a list of numbers that your new number is bigger than, and a list of numbers that your new number is smaller than, like a sandwich. For a simple example, you could define 1/2 this way. I want a number that is bigger than 0, but smaller than 1. Boom, you've defined 1/2 into existence. Now, here's a more interesting example. I want a number which is bigger than 1, 2, 3, 4, 5, and so on. We're allowed to leave the other lists blank. So, we just defined a number into existence which is bigger than any natural number. That means it's infinitely big. Coolio. Surreal numbers like ordinals use omega to represent infinity. Now here's another number we could define into existence. I want a number which is bigger than 1, 2, 3, and so on, but smaller than omega. Well, this number is also infinitely big, but it's less than omega. We just defined infinity minus 1 into existence. We could do the same thing to define infinity minus 2 and infinity minus 3, and so on. But now, get ready for this. I want a number which is bigger than 1, 2, 3, and so on, and is smaller than omega, omega minus 1, omega minus 2, omega minus 3, and so on. This is going to define into existence a number which is halfway between 1 and infinity. Infinity divided by 2, or 0.5 times infinity. Coolio! You can do some other fancy maneuvers to get like 2 times infinity, pi times infinity, or any real number times infinity. Those are all valid surreal numbers distinct from 1 times infinity. So, infinity in the surreal numbers is not limited by the absorption property. In fact, you could do all sorts of stuff with surreal numbers, like negative infinity, infinity squared, 1 divided by infinity, infinity to the power of 1/10 of infinity cubed plus 1. The list just goes on and on. The surreal numbers are super flexible. And get this, there's a sense in which the real numbers, the ordinals, and the cardinals all live inside the surreal number system. Surreal numbers are kind of like the final boss of numbers. Anyways, how well do surreal numbers work with decision theory? Well, since the real number line already exists within the surreal numbers, when you change utilities from real numbers to surreal numbers, literally nothing with standard decision theory breaks or even changes. 1.3 exists as a surreal number, and when you multiply it by 0.6, you get 0.78. But on top of that, the surreal numbers lack the absorption property, so omega is bigger than omega times 1 in a million. So our extended decision theory would tell us to press button A in that thought experiment I mentioned a while ago. But on top of all of that, subtraction also works with surreal numbers. What's omega minus 0.1 times omega? Exactly what you would expect, 0.9 times omega. So we could use surreal numbers to model even the weirdest scenarios, like what if pressing a button has a 90% chance of giving you infinite reward, but a 10% chance of giving you infinite punishment? Surreal numbers can do it all. So, with our extended decision theory in place, we can now assess how Pascalian reasoning would work. Again, simplifying things a bit. You would assign a surreal number to the utility of each possible religion on the table, and then multiply it by the probability that the religion is true. The resulting surreal numbers are the expected utilities of those religions, and you should follow the religion with the highest expected utility. Now, what's interesting is that in this setup, it's still important for apologists to give arguments that Christianity is true, rather than, say, Islam, because if the probability of Christianity is too low, it will have a smaller expected utility than Islam. So modifying decision theory with surreal numbers to run Pascal's wager doesn't involve giving up rationality and blindly following a religion with no regard to evidence. Rather, it gives us a systematic framework for quantifying the infinite value that comes from pursuing God. Anyways, there's still a lot I could talk about, but that's the end of this video. Thanks for watching, I'll see you in the next one.